Welcome back, everyone, to Exploring Quantum Physics. Now we're going to complete the solution of the hydrogen atom according to classical mechanics. And this brings in the identification of a non-trivial constant of motion. This is something that was known for many years by people studying planetary motion, but emerged as something of great importance in the development of quantum mechanics. And I think you'll see that it points one to directions that are very fruitfully used when one goes to solving the Schrödinger equation for complex systems. Well, we'll see. Now, just to remind you where we are, we're still working on, we're leading up to the Bohr model of the atom by solving the classical problem. So when you do the homework, you'll probably be reminded of some of this material. Again, I just like to keep in view that our objective is to understand real physical systems. Maybe some of you are tiring of seeing these spectral lines, but I never get tired of them. Okay, here's where we left things at the end of the last lecture. We have these two constants of motion, energy and angular momentum, and that means that we know that if whatever the initial configurations of the particles are, they move in a plane that's determined by their initial orientation. And then the motion in that plane is also restricted to have a constant energy. So that basically there's going to be an orbit in the plane because there's not you can't have a sort of a continuous well, at any given point there'll be some limits in the motion that are determined by the energy, as we shall see. Okay, now how do we make progress? Well, we started with these two first-order equations of motion. Now, we then, for the vectors r and p, then we took scalar products. You might say r is a scalar. R is the square root of a scalar product. And we found that there was a conserved quantity, the energy, that just depended upon the scalar products of the vectors with themselves. Then there was a vector constant of the motion, an angular momentum, r cross p. That's also constant in time. Well, what other things do we have to look at? Well, from the value of angular momentum, we know that r and p lie in a plane. So what other independent vectors do we have that might lie in the plane? I think you'll easily see that these two, r cross L and p cross L, both lie in the same plane as r and p. So maybe there's some advantage to, and they're independent variables, maybe there's some advantage to looking at the equations of motion when framed in terms of these two new vectors. Because after all, since they lie in the same plane, that's quite possible that there's a simpler relationship between all four of these vectors than meets the eye right now. Okay, let's see what progress we can make. So let's take r cross L and look at it in greater depth. So then we can just say that's simply that, r cross p, which is then just substituting for r and r dot takes that form. Now we're going to invoke well-known vector identity. This is the so-called back cab rule. Again, this is something which this is going to come up again in the quantum theory of angular momentum, so it's a good idea for at least to be aware that such a thing exists, and then later on we'll see how you'll develop a sort of vector calculus that will help you easily rederive it. So this is how when you have two cross products, you can reduce them and simplify them, and so that gives when one goes through the math, here's this, just rewriting that identity. Then from the back cab rule, you get something that's proportional to the position vector and the velocity vector. And now a remarkable thing happens when you simplify this, and I think it's really worth your writing notes on this, or freezing the screen, pausing the screen, and taking yourself. This is a very elementary derivation, just a sequence of simple steps, and you see what it gives you is that R cross L is the time derivative of the unit vector times R cubed. Now, what about P cross L? Let's look at its. Let's look at the time derivative of P cross L. So that is just. I mean, this is an obvious identity since L dot is 0, and so we now get another cross product for R cross L. So in other words, well, let's just see where that takes us. So you see that R cross L is equal to R cubed times the unit vector of R dot. So this this equation implies that R unit vector dot is equal to minus R cross L divided by R cubed. But you see, that's what we have here. So that means that this vector, the sum of P cross L and the unit vector of R, is a constant of motion. This is often called the Runge Lenz vector. There's a Wikipedia article on this that's very useful, very readable, very informative. But I hope I've given you a path to re-deriving it. Actually, when you know that something exists, when you know that there's something involving P cross L that results in a constant of motion, then you should be able to calculate it again for this system. Now, the remarkable thing, here we are, we have the energy, we have the angular momentum, we have the Runge Lenz vector. The remarkable thing is that in some sense, the identification of the Runge Lenz vector solves the problem for us. Because, look at this. Let's calculate the scalar product of R dot A, which is RA cosine phi, if this is R, and that's A, and that's phi. So we know, first of all, we know that A lies in the same plane as R and P, and so we now know. So that means that the location of R is more or less precisely defined by the angle phi. Okay, but now taking R dot A from here, using this identity, say RA cosine phi is this quantity here. Now here is one of these vector identities, A dot B cross C. I hope you will recognize what to do with that. And in fact, you can use, if you can recall that identity, you can use it to complete the inline quiz, or you can try computing that directly yourself. And in any event, let's have a look at the quiz. Okay, so dealing with this, it's A dot B cross C. There's a cyclic identity. That's equal to, let's say we move everything around cyclically. That's equal to C dot A cross B. It's equal to B dot C cross A, and so on. And so, in other words, this term just reduces to the square of the angular momentum. And so now, let's see, I'm sorry for making such a mess here. Let's try to get rid of it. It's a very straightforward derivation. Well, now you see we have a very simple equation that relates r and phi. Thusly. So here is an equation that defines the orbit. It shows r as a rather simple function of the angle phi, and that's apart from specifying the origin of time, or once you have the values of these constants of the motion, things pretty much fall into place. So let's see, we've gone on for quite a while. So one final calculation that we'll do here. We have, this is, by the way, this is an orbit which can be a circle, an ellipse, or a hyperbola. And the distinction between those depends upon the energy. So there's one last calculation that is worth doing, and that is to calculate a squared. And I'm going to leave that to you as an exercise. It's worth doing because it's a fairly straightforward calculation. And that calculation gives us a relationship between the magnitude of A and the energy and the angular momentum. So in other words, the energy, the angular momentum, and the Runge Lenz vector are each constants of motion, but as this equation shows, they're not entirely independent. Okay, forgive me, but this is literally the last of the inline quizzes for the moment, and what it's going to be used for is to show you the significance of the value of the energy. In other words, for this system, as we'll see, the energy can be any, well, let's just take the quiz. So I hope you persuaded yourself that the energy of this system can be absolutely anything from between minus infinity and infinity. For example, you can have the momentum vanish at some given time. Let's say you just have these godlike powers for specifying the initial conditions. You can keep p at 0 and then bring the particles arbitrarily close together and get an arbitrarily large negative energy. Or you can move to some finite value of r and then crank up the value of p to whatever you need. You can make it as positive as you like. And once you fix the energy, it stays that way for all time. Now the critical thing to remember, this has to do with some of the readings in the supplementary material that'll be on the homework, is that there's a separate point of separation between positive energies, or between negative energies and positive energies. So when the energy is less than 0, all the orbits are elliptical. So these are like the orbits of the planets about the sun. You can get to highly elliptical orbits that are far distance away. Those orbits have negative energies, but they're approaching 0. For E greater than 0, you have a type of trajectory where, let's say here's the proton, the electron comes in and it just visits once and never leaves. So these two types of classical orbits actually have counterparts in the quantum mechanical spectrum,